A conducting bar with mass 25 kilograms and length 50 centimeters slides over horizontal rails that are connected to a voltage source. The voltage source maintains a constant current of 2000 amps in the rails and bar. A constant uniform vertical magnetic field of 0.8 Tesla fills the region between the rails. In part A of the problem, you are asked to find the magnitude and direction of the net force on the conducting bar. Ignore friction and electrical resistance. In part B, you need to find the distance d that the bar must move along the rails from rest to attain a speed of 100 meters per second. Let's start with part A and redraw the figure given by the problem as if we are looking at the rails and the bar from above. So these are the rails and this is the bar as seen from above. They are in a constant magnetic field that's coming out of the page, and there is a current I that goes through the rail and through the bar. The problem gives us the magnetic field, the length of the bar, the current through the bar and the rails, the mass of the bar, and the speed of the bar. We need to find the magnitude and direction of the net force on the conducting bar. Well, the only force acting on the bar is the magnetic force applied by the magnetic field B. This magnetic force is calculated as the current times the cross product between the length of the bar and the magnetic field B. We can rewrite this equation in scalar form, remembering the definition of the cross product. So the force will be equal to the current multiplied by the magnitude of the first vector, which is the length of the bar, multiplied by the magnitude of the second vector, which is the magnetic field B, multiplied by the sine of the angle between them. Well, the bar has this direction and the magnetic field is coming out of the page. Therefore, the angle between them is 90 degrees and sine of 90 is 1. So we can calculate the magnetic force or the net force on the bar as the current multiplied by the length of the bar multiplied by the magnetic field. All we have to do is replace each one of these quantities with its value. Current is 2000 amps, the length of the bar is 50 centimeters or 0.5 meters, and the magnetic field is 0.8 Tesla. This gives us a value of 800 newtons for the magnetic force acting on the bar. This magnetic force will be oriented to the right according to the right-hand rule. Remember, the magnetic force has to be perpendicular to the length of the bar, for which the direction is the same as the direction of the current, and the magnetic field B. Now, in the second part of the problem, we need to find the distance that the bar must move along the rails from rest to attain a speed of 100 meters per second. We have to connect the distance and the speed of the bar. Well, the bar is moving because there is a magnetic force acting on it, and that magnetic force does work. As a result of that work, the speed of the bar changes from 0 to 100 meters per second. Therefore, we can simply use the work kinetic energy theorem that says that the work done by all forces acting on the bar, in this case just the magnetic force, equals the change in kinetic energy of the bar. The change in kinetic energy can be written as the final kinetic energy minus the initial kinetic energy. Well, the initial kinetic energy is 0 because the speed of the bar is 0. And the final kinetic energy can be written as 1/2 mass velocity squared. Now, the net work done by the magnetic force can be calculated as force times displacement because the force is constant. And therefore, we write net work equals kinetic energy. All we have to do now is replace the force with its expression, and we will have current, length, magnetic field, which is the expression for the magnetic force, multiplied by the distance d, equals 1/2 mass velocity squared. From there, we find the distance as mass velocity squared divided by the current, the length of the bar, times the magnetic field multiplied by 2. Plug in the numbers for each one of these values. The mass is 25 kilograms. The speed of the bar is 100 meters per second. Don't forget to square it. The current is 2000 amps, the length of the bar is 0.5, and the magnetic field is 0.8, and I'll multiply it by 2, and that gives me 1.6. The distance that this bar would need to travel to attain a speed of 100 meters per second is 156.25 meters. As you can see, this is a very long distance, so they are really not useful for accelerating objects.